So actually we have stopped here. We had discussed about the 4 laws: Kirchhoff law, Planck's law, Wien's displacement law, and Stephen Boltzmann's law. Law. So thereafter, next topic is intensity of radiation. Intensity of radiation is a very important term in your module. Intensity of radiation. Intensity of radiation. So intensity of radiation simply means that അതിന്റെ എന്താ പറയുക റേഡിയേഷന്റെ പവർ കാണിക്കുന്നതാണ് intensity of radiation എന്ന് പറയുന്നത്. So it can be defined that radiation intensity of radiation can be defined as rate of energy leaving a surface in a given direction per unit solid angle per unit area of emitting surface normal to the mean direction in space. കുറച്ച് വലിയ ഡെറിവേഷൻ ലെങ്ത് ആണ്, പക്ഷേ ഐഡിയ മനസ്സിലാക്കിയാൽ അതിന് ചെറിയ ക്വസ്റ്റ്യൻ മാത്രമേ ഉള്ളൂ. ഇതിന്റെ എന്താണെന്ന് ചോദിക്കാൻ സാധ്യത കുറവാണ്. സോ നമുക്ക് അതിന്റെ തിയറി എഴുതുമ്പോൾ നമുക്ക് ഇറ്റ് ഈസ് ഡിഫൈൻഡ് ആസ് intensity of radiation can be defined as a rate of energy leaving a surface, which means a radiation. Rate of energy leaving a surface in a given direction, in a particular direction, in a given direction per unit solid angle. Per unit solid angle. Here we want solid angle per unit area of emitting surface. Per unit area. Per unit area of emitting surface. Normal to the mean direction. Normal to the mean direction. So simply means I. I is the rate of energy. Simply says that is a rate of energy, intensity rate of energy leaving a surface, which is the radiation at a given direction, in a particular direction per unit solid angle. So what is solid angle? Solid angle എന്താണ് അടുത്ത് പറയാൻ പോകുന്നത്. So solid angle per unit area of emitting surface normal to the mean direction. So what is solid angle? Solid angle refers to solid angle എന്താണെന്ന് പറഞ്ഞിരിക്കുന്നത്. So what is solid angle? സോളിഡ് ആംഗിൾ എന്ന് പറഞ്ഞാൽ ഡയറക്ഷൻ നമ്മൾ വിചാരിക്കുന്നത് ഇന്റൻസിറ്റി ഓഫ് റേഡിയേഷൻ വിത്ത് റെസ്പെക്ട് നോർമൽ ഉണ്ടാക്കുന്ന ആംഗിൾ ആണെന്നില്ല. ഇറ്റ് ക്യാൻ ബി ഡിഫൈൻഡ് ആസ് പോർഷൻ ഓഫ് ദി സ്പേസ് ഇൻസൈഡ് എ സ്പിയർ. I will draw a particular figure here. XY Z axis. And I am drawing a particular sphere here. Total, we can call it as a total sphere. Total sphere under the XY Z total consideration as whole sphere, and we are taking a small section of sphere here. Here. Okay. Total sphere under that is a section മാത്രം എടുക്കാം. Okay. I am taking a small section and extending this particular axis here. Okay. Then as and we are assuming that the particular radiation is happening from the mean portion or center of this portion, center of the sphere and പുറത്തോട്ടേക്കാണ് radiation നടക്കുന്നത് consider ചെയ്യുക. We are considering that radiation is emitting from the particular center of this particular surface, center of this total sphere. ഒരു ചെറിയ ഭാഗം എടുത്തിരിക്കുന്നു. ഓക്കെ, ഇങ്ങനെ എടുത്തിരിക്കുന്നു. സോ we are assuming that a particular direction is radiation is emitting from the center of the sphere to the external surface. So it is a radius. And this is the emitted radiation. Emitter radiation is the radiation. Okay, and its particular surface is the outer surface of the sphere, which is the radiation collector. So we can assume that it is a surface. Which emits the radiation. We can take it as a spherical surface which emits the radiation from the center of the sphere to outside, and we are taking a particular that particular radiation മൊത്തത്തിൽ പോകുന്ന ഒരു കോൺ. Total radiation from the center of the sphere is happening at a particular radiation. Then that angle, that spherical angle is known as solid angle. Okay, spherical angle is known as solid angle. So solid angle is defined as the portion of the space inside a sphere enclosed by a conical surface with the vertex of the cone at the center of the sphere. With the vertex of the cone at the center of the sphere, and we describe the particular solid angle as the portion of the space, portion of the space inside a spherical enclosed cone. Inside a sphere enclosed by a conical surface, which is vertex is a point at the center of the sphere, and this is called as solid angle. Okay, solid angle is the space inside a sphere, enclosed by a conical surface, which means a solid angle, by a conical surface with the vertex of cone, that means at point, vertex of cone at the center of sphere, denoted by dw, that particular solid angle is denoted by the intensity of radiation is denoted by I, intensity of radiation I. Okay, I. Intensity of black body is IV. Okay. Then that what is a solid angle? Particular solid angle subtended by the complete hemisphere. Solid angle subtended by total hemisphere is denoted by 2 pi. 2 pi. 2 pi is the angle, total angle subtended by the total sphere. Total angle. Total angle is 2 pi. This is the total angle subtended by a sphere. Total solid angle subtended by a sphere is 2 pi. And we are taking the particular small conical surface, which is a radiation conical surface. Okay, and that for a particular radiation, happening in a particular surface and a particular direction, we are taking that particular area and what particular conical surface only, which the vertex is subtended by the center of the sphere, and that particular angle subtended by that radiation is called as solid angle of that radiation. Okay, solid angle of that particular radiation. Then what is the equation for, and what is the particular equation for intensity of radiation? Intensity of radiation പറഞ്ഞു അതിന് അതിൽ solid angle വരുന്നതുകൊണ്ടാണ് solid angle എന്നാണ് പറഞ്ഞത്. Okay, that is solid angle. And what is intensity of radiation? Intensity of radiation possesses the equation. There is small derivation. We are not doing that particular derivation. I will give you the derivation in the sake of note as a PDF. Like third module, fourth module, PDF file തരാം. And we are only simply writing that particular equation only. That is, we can relate the particular equation in intensity radiation, and we can relate the particular equation into emissivity. Emissive power is related to the equation. Emissive power E equal to pi into I. Okay, that is total emissive power equal to pi times intensity of radiation. So we can calculate the radiation intensity by E by pi. I equal to E by pi. Okay, intensity radiation I equal to E by pi, and total emissive power equal to pi times intensity radiation, and we can write that I equal to E by pi. So we can do a problem. Okay, problem for apply the particular equation and particular laws we are studying. Okay, so please start on a simple problem related to this particular topic. The topic is a problem topic end. So question, please learn the question. The effective temperature of a body having an area of 0.12 meter square. 0.12 meter square is 527 degrees Celsius. The effective temperature of a body having an area of 0.12 is 527 degrees Celsius. Calculate the following. total rate of energy emission. First one, total rate of energy emission. Total rate of energy emission, that is energy power. Energy emission. Second question, intensity of normal radiation. Intensity of normal radiation. Intensity of normal radiation. And third one, wavelength of maximum monochromatic emissive power. Wavelength of maximum monochromatic emissive power. So how we can calculate the following question, following terms, that is rate of energy emission, intensity of energy normal radiation, and wavelength of monochromatic emissive power. The only given data are area equal to 0.12 and temperature T equal to 0.12 meter square and temperature is equal to 527 degrees Celsius. 527 degrees Celsius equal to 527 plus 273 equal to, convert, 800 Kelvin. 800 Kelvin. Temperature is 800 Kelvin and area is 0.12 meter square. So first question is total rate of energy. Total rate of energy. Rate of energy emission, which means simply E. E equal to by Stephen Boltzmann's law. By Stephen Boltzmann's law, total emissive power equal to, by Stephen Boltzmann's law, total emissive power equal to sigma T raised to 4, right? Sigma into T raised to 4 when we are taking a unit area, right? When we are taking unit area, we have the equation sigma A T raised to 4. Sorry, sigma T raised to 4. So when we are considering a particular area here, we can write the equation as sigma A T raised to 4, right? We are taking that Stephen Boltzmann's equation by taking as area equal to constant or area equal to unity, area equal to 1. So when it is not considering that area equal to 1 and particular area has a value, we can take the equation as sigma A raised to T raised to 4 by Stephen Boltzmann equation. EB equal to sigma A T raised to 4, right? So sigma is the value. We have the constant value. We have another 5.67 into 10 raised to minus 8, right? Sigma value is a Stephen Boltzmann's constant, that is 5.67 10 raised to minus 8. So 5.67 into 10 raised to minus 8 into area 0.12 into T raised to 4, that is 800 raised to 4. Okay. 800 raised to 4. So we will get the energy or total power energy rate of energy as index watt. Watt equal to that is the value 2786.9 watt. 2786.9 watt. The value in watt. Okay. So the first question is done. The second question is intensity of normal radiation. So intensity of radiation, we know that intensity of radiation equal to I equal to EV by or E by or EB. Both are same. EB by, for a black body are EB in the okay. So E equal to E pi. I equal to EB by pi. So what is the value of E? Whether you want to take the value of 2786, that particular value on the kind of I equal to EB by pi is the equation. Whether you want to take the equation of EB, right, same equation like that. Please look at the explanation for intensity of radiation. Like, look at the intensity of radiation definition. Please read the intensity of radiation definition. That rate of energy leaving a surface at a given direction per unit solid angle per unit area. Per unit solid angle per unit area. So intensity of radiation can be taken only for a unit area. We are considering that intensity of radiation for a normal radiation that for unit area, per unit area. So area equal to 1 ആണ്. Okay, so we can that particular area ഇല്ലാത്ത equation എടുക്കേണ്ടത്. Okay, here particular rate of energy emission. Rate of energy means that particular rate കണ്ടുപിടിക്കണം. So the area is given for a ചെറിയ ഏരിയ അല്ല, total area for a rate of energy for a total area that you got to find. That is sigma a raised to a into t raised to 4. For intensity radiation, the definition is the particular in rate of energy per unit area. That is the definition for intensity radiation. So we want to take the equation of sigma t raised to 4 only, EV, not area. By Stephen Boltzmann's equation, you only want to take the sigma t raised to 4 per unit. The equation will be got by per area, per meter square, okay, by temperature, by pi 3.14. That is 5.67 into 10 raised to minus 8 into 800 raised to 4 divided by 3.14. Okay, that is the value for intensity of normal radiation. Intensity. The equation rate of energy equation is 287 per watt in the unit of watt. Here we will get the equation watt per meter square. That is per meter square, per area, per unit area, per unit area. That is 7392.5 watt per meter square. 7392.5 watt per meter square is the value of intensity radiation in the case of. Okay, അങ്ങനെയാണ് ചെയ്യുന്നത് മനസ്സിലാക്കും. And third question is to find wavelength of maximum monoclinic emissivity. Wavelength of maximum monoclinic emissivity. So what is the wavelength for a maximum monoclinic emissivity? Lambda max. Right? Lambda max. Lambda max. You want to find the value of lambda max. Wavelength of maximum monoclinic emissive power. So according to that particular equation, what equation? According to Wien's displacement law. According to Wien's displacement law. According to Wien's displacement law, we know that lambda max into t equal to constant, right? According to that particular law. What is the law? Wien's displacement lambda max into t equal to constant. Okay, and lambda max into t has a value that if I derive that 2898 micrometer, right? 2898 value is there. So lambda max into t is a constant according to Wien's displacement law, and you also know that lambda max into t equal to 2898. 2898, right? Micrometer Kelvin. So lambda max equal to 2898 divided by t. 2898 divided by t. Micrometer Kelvin. Micrometer Kelvin. And this equation is micrometer Kelvin divided by Kelvin unit. Right? Micrometer Kelvin is unit for 2898 and K is unit for temperature. And the K and K get cancelled. The equation will be 2898 divided by 800 watt micrometer only. Micrometer only. So 2898 divided by 800. 2898 divided by 800. Maximum monoclinic emissivity power means lambda equal to lambda max. So equation will be 3.622 micrometer. 3.622 micrometer. Okay. 3.622 micrometer. This is the application of suitable laws. Application of suitable law that the question will be asked more and more complex type, more and more complex from that You want to find out the particular lambda max value, temperature value, that a sigma value is constant value, temperature value, EV value, E value, intensity of radiation, etc., etc., etc. So we want to apply the 4 laws in several equations, several problems. So we want to be thorough with the particular values. It will be given in data book. It is there in data book. So please study thoroughly according to or relating the data book for the exam. Okay, അല്ലേ? ശരി. Then also ഒരു പ്രോബ്ലം കൂടി ചെയ്തിട്ട് നമുക്ക് വൈൻഡ് അപ്പ് ചെയ്യാം. A simple problem, a two-line problem. ചെയ്ത് വൈൻഡ് അപ്പ് ചെയ്യാം. Next question. Assuming the sun to be a black body, emitting radiation with maximum intensity, emitting radiation with maximum intensity at lambda equal to 0.49 micrometer. 0.49 micrometer. Maximum intensity at 0.49. That is lambda max equal to 0.49. Okay. Calculate the following. Okay. This question is asked like that. That assuming sun to be a black body. Sun is considered as a black body and emitting radiation at maximum intensity at lambda equal to 0.49. That is lambda max equal to 0.49. Simply calculate the following. First one, surface temperature of sun, T. Surface temperature of sun or black body. Surface temperature of sun. And second question is heat flux at the surface of sun. Heat flux at the surface of sun. EV value ആണ് ചോദിച്ചിരിക്കുന്നത്. Black body of sun or E of sun അല്ലെങ്കിൽ E of black body. Question is asking the rate of energy, rate of emissive energy, rate of energy distribution or heat flux, etc. All means that the value to be find out is EV or E value, emissive power. Okay, വേറൊരു വാല്യൂ നമ്മൾ എടുത്ത് പഠിക്കുന്നില്ല. So it is given that given value is lambda max equal to 0.49 micrometer. Lambda max. Okay. So first question is to find the surface temperature of sun, T. Surface temperature of sun or black body, T. So we know that simple derivation is simple substitution equation. That is lambda max into T equal to 2898 micrometer Kelvin. You know that. So we can directly find the value of T here. Lambda max value is given. So T is equal to 2898 divided by temperature is given as, so temperature is not given. Lambda max is given as 0.49. So we will get the temperature in Kelvin. We will get the temperature as Kelvin as അല്ലേ? അങ്ങനെ യൂണിറ്റ് കെൽവിനിലേക്ക് വരുന്നത് മനസ്സിലായോ? ടെമ്പറേച്ചർ യൂണിറ്റ് കെൽവിൻ നമുക്കറിയാം, പക്ഷെ എങ്ങനെയാണ് കെൽവിൻ നമുക്ക് കിട്ടുന്നത് നമുക്ക് പറഞ്ഞുതരാം. അതായത് 28 divided by 0.49 is 5914 or something like that. 591314 അത്ര നിങ്ങൾക്ക് കിട്ടുന്ന വാല്യൂ എത്രയാണെന്ന് ചെയ്തത്. ഓക്കെ, കിട്ടുന്ന വാല്യൂ എഴുതുക. ആൻഡ് ദ യൂണിറ്റ് ഈസ് ഹിയർ കാൽക്കുലേഷൻ is equal to lambda max into 2898 in equation done micrometer Kelvin divided by lambda max in the equation micrometer. We are cancelling micrometer, we will get the unit as Kelvin. അങ്ങനെയാണ് ഓരോ ഇക്വേഷനും യൂണിറ്റ് വരുന്നത്. You will get the equation as 5914 Kelvin. Very big temperature. This temperature of sun is very higher. Okay. And second question is to find the heat flux at the surface of sun. സണ്ണിൻ്റെ ഏരിയ ഒന്നും കണ്ടിക്കാൻ നമുക്ക് പറ്റില്ല കേട്ടോ. We cannot find the area of surface of sun, and we don't have an equation to find the area of surface of sun. Okay, the area, if it is given in a question, you can use. So the area is not given in a question, and we cannot calculate the surface area of sun. So we can use the equation as E equal to A sigma T raised to 4 1 sigma T raised to 4. Sigma T raised to 4. Simply E equal to sigma T raised to 4 or E sun. E sun. Here black body is sun. So either we can use the EB value or E sun. Anything. So E sun is sigma T raised to 4. That is T is given as 5914. Sigma is given as 5.67 into 10 raised to minus 8. We know the value. 10 raised to minus 8 into T raised to 4. T raised to 4 means 5914 whole raised to 4. Simple problem. It is a simple problem, and I'm detailing the particular problem to understand, to make you to understand the application of suitable laws. That 4 laws we have studied in a problem. Okay. 5914, that is the equation, question, the value that got in the textbook is 6.936 into 10 power 7 watt per meter square, right? Area is not given, so per meter square into 10 power 7. Okay, negative value. Okay, that is the method to find out the value of the particular T value, lambda max value, EB value, I value, etc. etc. That is the first section of this particular module to find out the value of heat flux or emissivity, emissive radiation. So we emissivity equation E by EB, emissivity equation also we had know that. Okay, and the textbook this particular question is done like that. That is 5.67 into 10 power minus 8 into 5914 raised to 8. Okay, 5918. So that's ഇങ്ങനെയാണ് 5.67 into 5918 or 5914 divided by 100 whole raised to 4. Okay, this is the method that done in your textbook. This രണ്ട് സെയിം ആണ്. ഓക്കെ, രണ്ട് സെയിം ആണ്. That is 10 power minus അടിയിൽ പോകുമ്പോൾ 10 raised to 8. 10 raised to 8. Question will be 10 raised to 8. Or we can write at 100 raised to 4. 10 raised to 8 or 100 raised to 4. So we can relate the both upper numerator. That is in numerator there is 5914 raised to 4. Denominator 100 raised to 4. So I combine the both equation into 5914 divided by 100 all raised to 4. The both are same. So we don't want to do particular complex step and substitution. Simply write the particular equation and calculate the value. So this is the method to find out the value of E lambda x, lambda or lambda maximum, temperature, or inner zero radiation I. Okay. So that is for the, this particular session. And for the next session, we can move to the next topic, that is configuration factor or shape factor. Configuration factor, shape factor for the next section. Okay.